In the previous video, we discussed all of the steps in creating a hypothesis test. There were 7 steps, and we're going to run through those again. So let's do another example. In 1994, 52% of parents of children in high school felt it was a serious problem that high school students were not being taught enough math and science. A recent survey found that 256 of the 800 parents of children in high school felt it was a seriously wrong problem that high school students were not being taught enough math and science. So do parents feel differently today than they did back in 1994? So let's just quickly jot down some data that we have up here before I even get started. Okay, so back in 1994, 52% of parents felt that math and science wasn't being taught enough. Now, we're going to fast forward into a recent survey. So now we're going to go into the future and we're going to do a recent survey. And we found that 256 of 800 felt that parents felt that teachers weren't teaching enough math and science. Well, when I put that into my calculator, I'm getting that is closer to 32%. Clearly, there is a vast difference between those two numbers. So at first glance, it looks like my survey, I did have quite enough people in there. That's a large survey, and I got drastically a number that is different than the original survey. So at first glance, I think that this survey is enough to prove that this is no longer the case. But we can't just state that by eyeballing it. We have to run through the 7 steps to prove, in fact, that 32 is unique enough away from this average or this claim that we can state that this is no longer the case. So that's kind of the process that we're going to be going through right here. Okay? So remember, step 1 was to meet the requirements. There are 3 requirements that we have to first meet. First, we have to determine whether the original distribution is normal. Is n times p times 1 minus p greater than or equal to 10? Well, this is p, and this is p hat. So in the original normal distribution, we have to figure out if n, which is 800, times p times 1 minus p. When I put that in my calculator, I get a number really close to 200, which is certainly greater than or equal to 10. So definitely we come from a normal distribution, which means we can make the normal distribution curve. Then we have to state that the samples are random and they must be independent. So somewhere in the paragraph, we have to make sure that the 256 of the 800 were randomly selected. Now, it doesn't state that, so we'll have to assume that that is true. We also have to prove that the sample is independent. Is the 800 less than 5% of all students in the country? And clearly that is true. Okay, so the requirements have been met. Now it's time to make our null and our alternate hypothesis. Our null hypothesis is stating that the original claim is that the true proportion is 52%. We're going to state something different. Remember, the p in the 52 stays the same. The only thing that changes is the sign in the middle. We're trying to prove what? It says, do parents feel differently? Differently means just simply not equal to 52% anymore. I'm not stating that they feel less or more than, just simply not that value any longer. Then comes our level of significance. It was given to us in the problem. We are trying to use a 5% risk of making an error, or type 1 error. In step 4, we find our test statistic. Z is our test statistic. We take p hat minus p over the square root of p1 minus p over n. P hat we found over here, which was 0.32, minus the original p, which was 0.52, all over 0.52 times 1 minus 0.52, all over n, which was 800. And we put this in our calculator, I'm getting a really low z value of negative 11.32, which again is my test statistic. So in step 5, I need to find the probability. Okay, so we're going to look up negative 11 as a z-score in my table 5. Well, you're going to notice negative 11 isn't even on my graph. Our graph only goes up to a negative 3.4 value. So negative 11 is going to be way out here, and it's going to have an itty-bitty little probability associated with it. So what we'll do is we'll just use the smallest probability possible on my table. Okay, the smallest probability possible is 0.0002, and we know that it's got to be less than that. So we'll assume from the table that the probability is going to be less than 0.0002, but remember, this is a two-tailed test. It is a two-tailed test because we have the not equal. Not only is it going to be less than, but it also could be greater than. And so since this is a two-tailed test, we have two tails. We have to multiply that area by 2. And it doesn't really matter because this probability is still going to be very, very small. Let's look at a picture of what we know so far. We know in the middle we have our original claim is that 52% of parents feel math and science isn't being taught enough. We have a level of significance of 0.05. So this area right here is 0.05, and that's considered my reject area. Now if my sample falls in this area, I will reject the null. If my sample does not, and it falls out here closer to the original claim, then I do not reject this. So we're looking for unique evidence. Our unique evidence said my test statistic was negative 11, which is way out here, having a probability of this itty-bitty little area. I will do that in green. So a z-score of negative 11, which is results from the p-hat of being 0.32, has this itty-bitty little area out here, and this tiny little area is going to be smaller than 0.0004. And you can see that my sample is lying in this red reject area, which means we will end up rejecting the null hypothesis. And the reason is because my p-value is less than alpha. We will reject the null hypothesis. So in my conclusion, I will interpret what we've just done. In my interpretation, I will say that there is enough evidence at the 0.05 level of significance to conclude, and this is where we conclude our alternate. We're going to conclude that the proportion of parents with kids in high school who feel math and science is a problem has definitely changed. So now I think would be a good time to show you how to do all of this in StatCrunch. Okay, so in StatCrunch, we're going to do the same hypothesis test of the math and science problem that we just finished. So the first thing we do, just like we did with confidence intervals, we go up to Stat, Proportion Stats for one sample with Summary. And you'll notice that the information is the same, but instead of selecting confidence interval, we're going to select the hypothesis test this time. So in this example, we had 256 out of 800 that agreed that math and science wasn't being taught enough in schools. So we're going to do a hypothesis test, and we got to put in our null and our alternate hypothesis right here. We're stating that the null, the true proportion, was 0.52. And notice it already gives me the 0.52 down here. You cannot change that. All you can change is the sign in between. So do we want a two-tailed test, a left-tailed test, or a right-tailed test? For this example, we did a two-tailed test. And so we go to compute. It gives me, notice it gives me the sample proportion, which was 32%, and that's what we figured out at the top of the page. And it also gives me the lower and the upper limits as if this were a, I did do a confidence interval. Did I not click on hypothesis test? I didn't. I apologize. Whoops. Let's try that one more time. I got to click on hypothesis test. There we go. Still gives me the sample proportion, but this time it gives me the test statistic, and that's exactly what we found in our notes, which was negative 11.32, right on. It also gave me the p-value. The p-value was so small, it's less than 0.0001. We knew it was going to be small because it was so far off of my table 5 that I couldn't even find it. So since that p-value is so small, you still have to know what to do with that p-value. So StatCrunch only takes you this far. It only gets you to the point where you got a p-value. You still have to be able to make the conclusion from there. You still have to do steps 6 and 7, where you compare your p-value to your alpha and then conclude that we will reject the null hypothesis, and you need to be able to interpret that answer. Okay, so let's go back to the notes. We're now entering section 10.3, which we're going to be discussing hypothesis tests of a mean. So we've discussed proportions already, so now we're going to talk about means. And the steps are the same, but the equations may differ. So again, the basic steps are, first confirm your requirements. The requirements must be satisfied. The sample must be random, the population must be normal, or n has to be great enough so that the t distribution starts to look more and more like the z distribution. Also, the sample must be independent. So all of those three things have not changed from chapter 9 when we discussed those with confidence intervals. Then we determine our null and our alternate hypothesis, which determines what type-tailed test we have. You'll always be given your level of significance, and then you compute your test statistic. So this equation is a little different. You find your test statistic. We will use t because generally we do not know sigma. So since we don't know the population standard deviation, we generally will have the sample standard deviation. So we have to use the t statistic instead of the z one. We take our sample mean, subtract our population mean from our original claim in the null hypothesis, divided by your sample standard deviation, divided by the square root of the number in your sample. Obviously, we can use StatCrunch also to do this, using stat t-stats, one sample, which we will do at the end of the next example. Then we will use the student's t distribution table, which is table 6, to determine the p-value. Remember, if you have a two-tailed test, you must multiply 2 times that area. Then we decide whether we will reject the null hypothesis or not by comparing the p-value to the level of significance, and then we will interpret our answer. So it's the same steps from before. So let's go through an example using mean in our hypothesis test. So here we have a study that has been published in the American Journal of Psychiatry. Researchers wanted to measure the effect of alcohol on the development of the hippocampal region in adolescents' brains. The hippocampus is the portion of the brain responsible for long-term memory storage. The researchers randomly selected 12 adolescents with alcohol use disorders. They wanted to determine whether the hippocampal volumes in the alcoholic adolescents were less than the normal volume of 9.02 cubic centimeters. An analysis of the sample data revealed that the hippocampal volume is approximately normal with a sample mean and sample standard deviation given, and we're going to conduct the appropriate test at the 0.01 level of significance. Step 1. Are the requirements met? First, determine that the sample is random. So if this is not stated anywhere in here with the 12, oh, it is stated. We finally have one that actually states that it's random. So that we don't have to assume it has been checked. Then we have to decide whether it is normal. In order to decide that it is normal, the population must be normal. And I don't believe anywhere in here it talks about it does. It says the analysis of the data receives that the volume is approximately normal. Right there. So it's already been stated. Now, even if it didn't state that, we would have to have an n that is larger than 30. And we don't have an n larger than 30, so we wouldn't be able to state that it's normal. So I'm glad that they stated the fact that the population was normal to begin with. Then we have to state whether it is an independent sample. Well, our n, which is 12, has to be less than 5% of all adolescents. Clearly, 12 is smaller than that. Okay, so let's figure out what our null and our alternate hypotheses are going to be. This time we're dealing with mean. There must be a claim that is being made somewhere in this statement. It said up here, they wanted to determine whether the hippocampal volumes in alcoholic adolescents is less than the normal volume of 9.02. So the claim is that normal is 9.02, and we want to claim that something has changed from that. Alcoholic adolescents, we're trying to prove that they are less than normal. So we would say less than normal. So this is cubic centimeters, and this would be a left-tailed test. So step 3, we decide what our level of significance is. It was given to us in the problem, which is 0.01. We're willing to risk a 1% chance of making a type 1 error. Step 4 is to find your test statistic. Our test statistic is given by x bar minus the mean over s over square root of n. So our x bar is given from the problem. We stated out of the 12 adolescents, we found an average hippocampal volume of 8.1 cubic centimeters. The original or average of a normal brain was 9.02. The sample standard deviation was given as 0.7 divided by the square root of n, which is 12. So when I put that in my calculator, I get a t-value of negative 4.553, which again is my test statistic. Now what we do is we looked at information up in the table. But before I do, I always like to draw a picture. Okay? So we're actually going to go to table 6 to find this probability. Let's look at what we have so far. Now this is a T curve, not a Z curve, because we had to use the T distribution. And we know that the average, or the mean right here in the middle, the normal volume is 9.02 cubic centimeters. And we know that my reject area is going to have an area of 0.01. And since it's a left-tailed test, it's going to be over here. So this is going to be my reject area, and it's going to have a volume, or excuse me, an area of 0.01. So we need to find out if this test statistic lies in there or not. So we have to find the probability of this test statistic. So we're going to go to table 6, which is the T table. Now, in order to use the T table, we need degrees of freedom. Degrees of freedom is always going to be n minus 1. So we have to use degrees freedom of 12 minus 1, which is 11. Okay? So we're going to go to my T table, and we need degrees of freedom of 11. Next thing we need to know is the T. We already found the T. Now we need probability. So we go across this line until we find the T that is closest to the T that we found as my test statistic, which was 4.553. And we're not going to worry about the negative because right now it's only concentrating on the right-hand side with a positive T. The values would be the same on the left-hand side. So 4.553 is going to be just past this number, isn't it? Right? Just on the other side of this number, and the table doesn't even go that far. So my 4.553 is going to be just on this side of this number, which means my probability is going to be just on this side of this small number. Notice that my probabilities are getting smaller and smaller and smaller and smaller. So my probability is going to be even smaller than this number, 0.0005. So that means my probability is going to be something smaller than 0.0005. Or even if you assume it's that number, it's still going to be enough information. So if I come over here to my curve and I plot that information in green here, this probability certainly is a lot smaller than this. It'll be over here on the left-hand side where my sample mean was 8.10, which results in a z-score of negative 4.553, which has a small volume or area, which is something smaller than 0.0005. Okay, so this tiny little green area in this triangle certainly falls within that reject zone. So I have proven that my p-value is certainly less than my alpha. So that means we will reject the null hypothesis. So let's go back up to the top and let's remember what the null was. The null hypothesis stated that all adolescents have this volume of their hippocampal region of 9.02 cubic centimeters. We're stating in alcoholic adolescents, they have a mean that is less than that number. And since we are rejecting the null hypothesis, we now will state the alternate as our conclusion. So in step 7 in our conclusion, we would state that there is enough evidence, or there is sufficient evidence at the 0.01 level of significance to conclude. And then this is where you put your alternate hypothesis in. We are going to conclude that the mean volume of alcoholic adolescents hippocampal regions is less than normal. because normal was 9.02. And we are stating it is now less than normal. So let's try doing this one now in StatCrunch as well. Okay, so to do the StatCrunch from the previous example, we're going to go up to Stat, and we're going to use T-stats from one sample using the summary. So we're going to put our sample mean in there. We found the sample volume of the brain was 8.10 with a sample standard deviation of 0.7, and the sample size was 12. So we're going to conduct this hypothesis test, and we want to conduct it. The null hypothesis stated that the mean was 9.02. And we're stating that we now think it is less than that for alcoholic adolescents. And when we compute that, it automatically gives me my degrees of freedom. It gives me my t-test statistic, which is negative 4.55. We already found that. And it also gives me the p-value. We found that the p-value was less than 0.0005. In fact, it's 0.0004. Regardless which number it wasn't going to matter because it's going to be less than my level of significance either way. So let's do another example before we move on to something different. Let's try one more. This one is stating that the ACT is a college entrance exam. In addition to administering this exam, researchers at ACT gauge high school students' readiness for the college level subjects. For example, ACT has determined that a score of 22 on the mathematics portion of the ACT suggests that a student is ready for college level math. To achieve this goal, the ACT recommends that students take a core curriculum of math in high school, which is one level of Algebra 1, 1 year of Algebra 2, and 1 year of Geometry, which is generally taken in your freshman, sophomore, and junior years. Suppose a random sample of 200 students who completed this core set of courses results in a mean ACT score of 22.6 with a standard deviation of 3.9. Do these results suggest that students who complete this core curriculum are ready for college level math? That is, are they scoring above the 22 on the math portion of the exam? Okay, so first thing first, we have to meet the requirements. You guys should know the requirements by now. Is it random? We got to look for those words. Is it normal? And is it independent? So in order to determine that it's random, you have to look to see whether these 200 students were randomly selected, and it states right here that they were. In order to prove that it's normal, the original population distribution has to be normal. So we have to see whether there was a normal distribution originally. It doesn't state anywhere in the sentences that the population was normal, but we can assume that our sample distribution is normal because n certainly is greater than or equal to 30. So we can assume that this is, using the law of large numbers, approximately normal. Also, is it independent? Is the 200 students less than 5% of all people who take the ACT? And yes, it is. Okay, so what is my null and my alternate hypothesis? Well, the claim that is being made is that ACT has determined that a score of 22 is needed. So they're claiming 22 is the average that is needed on the test to say that you're ready for college level math. We're trying to claim something other than that. We got a random sample of 200 students who completed this core math courses, and they received a higher score. And we're asked if these results suggest that if you complete this core curriculum, you are ready for college math. So we're trying to prove whether they do better than the original 22 that was needed. Our level of significance was stated somewhere, and if it's not, we assume it is 0.05, and that's what we're going to have to do because the level of significance is not mentioned. So we'll assume 0.05 for this question. Step 4, this is where we find our test statistic. Remember, T is equal to your data minus your mean divided by your standard deviation. So for this example, our X bar was given to us as 22.6. That was the average score from those students in my sample. Now the average score is 22. That's divided by the standard deviation from my sample, which is 3.9, over the square root of n of 200. This is going to give me a sample test statistic of 2.176. So now what we do is we find the p-value associated with that test statistic. So we go over to table 6 and we find the p-value associated with this test statistic. In order to use table 6, we need degrees of freedom. Since there were 200 in my sample, that means my degrees of freedom is 199. So when I go to my T table, I look up a degrees of freedom of 199, and there isn't. So I pick the number closest. Instead of picking 1,000, I will pick 100. And then I go across that row until I find the T that is closest to my test statistic, which we found was 2.176. So 2.176 lies in between these two numbers here. So that means my probability is going to lie in between these two numbers here. So the probability, or the area in this curve, is going to be between 0.01 to 0.02. Somewhere in between those values. So when we go back to making a picture, let's look at a picture of what we have so far. We know on average, people will score 22 on the ACT. We know that the reject zone is going to be 5%. We need to find our test statistic and plop it in here in our graph. Since our probability is less than this, the area is going to be smaller. This area right here, which is my p-value, is only between 0.01 to 0.02, somewhere in that range. Because my t is 2.176, or 2 standard deviations away from the average, which means I have a x-bar of 22.6. Now, my conclusion that I will make is that my p-value is indeed less than my alpha, so I will reject the null hypothesis, meaning I have enough evidence. My sample was unique enough that it was far enough away from the average to conclude something different. So I will no longer conclude that that is the average. I will now conclude something different. I'm going to conclude my alternate. The alternate says if I take the core CLAP math courses that they suggest I should, you will end up with an ACT score that is higher than average of 22. So my interpretation would be that there is sufficient evidence. At the 0.05 level of significance. To conclude that completing the core math curriculum scores a student higher than a 22 on the ACT. So there's one more piece to this puzzle that I would like to discuss, and that's the difference between practical significance and statistical significance. The following example is going to illustrate the idea that large sample sizes can lead to results that are statistically significant but not practically significant. For example, the manufacturer of a daily dietary supplement claims that its product will help people lose weight. The company obtains a random sample of 950 adult males aged 20 to 74 who take the supplement and find that their mean weight loss after 8 weeks was 0.9 pounds, with a standard deviation of 7.2. So let's perform first a hypothesis test and determine, is a mean weight loss of 0.9 pounds statistically significant? Okay, so for right now, let's skip step 1. We'll assume all of the requirements have been met. Step 2, which is decide what our null and our alternate hypothesis is. Our null hypothesis is stating that the average weight loss, we'll just assume, is 0, meaning no weight loss at all. And we want to prove otherwise. We want to prove that there is a weight loss. In other words, you will lose more than 0 pounds. What we do next is we find our test statistic, right? Step 3 was the level of significance. We're going to use a 0.1 level of significance, and our test statistic is going to be T. T is equal to your X bar, in this case was the average from my sample, which was 0.9 pounds, minus the average weight loss, which we'll assume is 0. We're trying to prove that that's a difference, divided by the standard deviation, which was 7.2, over the square root of how many were in my sample? There was 950 adults. This is going to result in a T value of 3.85. Now, step 5 says I go to my table and I look up that T value. If I have degrees of freedom of 949, because that's one less than my sample size, and I go to table 6 with a degrees of freedom of 949, I'll use the closest number, which is 1,000. I find the T value, which is 3.85, which is off the chart, which means my probability is off the chart and is less than 0.0005. So my p-value is going to be less than 0.0005 because it's off the chart. Now we're going to note that my p-value is definitely less than my alpha, which means we will reject the null hypothesis. So we would state that there is sufficient evidence to conclude that the weight loss average was positive. We're concluding we rejected this null hypothesis. So we are concluding that the average weight loss was in fact greater than 0 or a positive number. This is statistically significant. And it's significant because we had enough evidence. Okay? Do you think that a mean weight loss of 0.9 pounds is worth the expense and the commitment of a daily dietary supplement for 8 weeks to lose 0.9 pounds. In other words, does the weight loss have practical significance? And the answer is no. It does not have practical significance because someone's weight could actually fluctuate by more than that in just a day. Oops, can't see that, sorry. So someone's weight can fluctuate by 0.9 pounds in just one day. So why would we advertise this product and say take this for 8 weeks? Because we can guarantee you will lose 0.9 pounds in 8 weeks. This is what we call not practically significant. So not practically significant. Just because we prove it works doesn't mean it's practical. So let's go ahead and do one more part. Let's test the hypothesis at the 0.1 level significance, but this time let's change our N down to 40. So before we had 950 subjects, now let's make it only 40. Okay? And let's see what happens to the p-value. So let's redo everything that we did up here, but the only thing we're going to change is the 40 down here. So I can leave all of this the same. In fact, maybe I'll just I'll get another piece of paper like this. Let's just redo this exact same question, but this time let's change N to being 40 instead. Okay? So we still have the same null and alternate. We still have the same level of significance, but this time our T is going to change to 40. That's going to give me a T value of 0.79. With the same degrees of freedom, if I go to my T table, which is table 6, and I look up my degrees of freedom with my T of 0.79, we're going to use degrees of freedom of 1,000, and again, my T value is 0.79, so it's somewhere in between these two values here. That means the probability in the tail is going to be somewhere between 0.20 to 0.25. So the p-value is going to be somewhere between 0.20 to 0.25. So it's quite large. It is now, if I were to compare it to my level of significance, it is now larger than my level of significance, meaning I would fail to reject. This time my p-value is going to be larger than alpha, so I will fail to reject the null hypothesis. So I'm not going to no longer reject that. I now cannot claim the alternate. I would actually conclude the null because I failed to reject it. So large samples can lead us to reject a null hypothesis even when there may not be practical significance. So be careful.